Let's continue with the freezing point depression and boiling point elevation colligative properties. And I already explained in my last video that if you have a pure solvent and you add some solute into it, then the freezing point of the pure solvent decreases. Let's say water is 0 degrees Celsius. If you're adding a solute, it will not freeze at 0, it will freeze at the temperature lower than 0 degrees Celsius. On the other hand, let's say the water boils at 100 degrees Celsius, and if you add a solute, the solute has to be non-volatile, and what it does is it elevates the boiling point. And as we can see, if the vapor pressure is getting lowered, of course the boiling point will increase. These are the formulas that are given to you. Look at example 11. Calculate the freezing point of a solution containing 0.135 moles of a non-electrolyte solute in 2.50 kilogram of benzene. There will be two more values that will be given to you in this question. The one is the pure temperature, freezing point of the pure solvent, normally pure solvent, which is benzene. So freezing point of the benzene will be given to you, which is 5.5 degrees Celsius. This will be given. And also the Kf value, which is a constant, freezing point depression constant, the value of that will also be given, 0.0540 molar. So now let's use the formula delta Tf equals Kf times m. I'm getting it from here. What is delta Tf? It is the freezing point of the solution minus the freezing point of the solvent equals Kf times m, molality. The freezing point of the solution, this is what we have to calculate. Freezing point of the pure solvent is 5.5 degrees Celsius. Kf value is 0. This is wrong, I'm sorry. That Kf value is 5.12 degrees Celsius over molar, my bad. Kf is 5.12 degrees Celsius over molar, and molality is moles of the solute, which is given to here. They're given in moles divided by the kilogram of solvent, and again it is given in kilograms, 2.50. So when you're going to do your math, solving the equation, your T solution should come out 5.2 degree Celsius. And we can see the freezing point of the pure solvent was 5.5 degrees Celsius, and when you added 0.135 moles of a non-electrolyte solute, the temperature, the freezing point, lowers down by 0.3 degrees Celsius. From 5.5 it is changing to 5.2. Again, there is no need for us to have a name of the solute right now, as long as we know it is a non-electrolyte. This freezing point depression and boiling point elevation, we can use these formulas to find the molar mass, of your solute. What do you have to do first? You need to know delta Tf or delta Tb in the case of boiling point elevation, these values. Once you know these values, from here you can use the formula this. Kf value is constant. Using this and Kf value or Kb value, you can find out the molality. Using the molality and mass of the solvent, you can find out the moles of the solute, and from the moles of solute you can find out the mass of the solute by dividing with the by dividing the mass of the solute by the moles. So one more time, this freezing point depression and boiling point elevation formulas we can use to determine the molar mass of your unknown solute. Let's say take the example of freezing point first. Using the first you have to find out delta TF, which is you find out by T solvent minus T solution. Once you have delta TF, you find out the molality by the formula delta TF equals KF times M. KF will be given. Once you find out the molality, then what is molality? Molality is the moles of solute by kilogram of solvent. That means using the molality and the mass of the solvent, you can find out moles of solute, and then you can find out moles of solute and the mass of the solute to find the molar mass of the solvent. Let's look at example 12. An absent-minded chemist pours 575 grams of a liquid solute into 1 liter of water, then leaves for the lunch. When he returns, he cannot remember if the liquid was methanol, ethanol, or butanol. If the solution boils at 106.40 degrees Celsius, which solute did he add? So, if I can find the molar mass of the solute, then I can find which solute it was. My very first step is to find, so here we are talking about boiling. That means I'm talking about boiling point elevation property. So in that case, my first step is to find delta TB. So what was that delta, if you T, so delta TB is equal to T solution, means the boiling point of the solution minus boiling point of the solvent, because solution is higher than solvent, remember it increases. Boiling point of the solution is 106.40, and boiling point of the pure solvent, what are we using? We are using water, so boiling point of water is 100 degrees Celsius. That means the change is 6.40. Now I'm done with first step, delta TB. Using this delta TB value, what will I do? My step number 2 is I will calculate molality. How? Delta TB equals KB times M. Delta TB is 6.40. Now KB, which is the boiling point elevation constant, its value will be given to you, which will be 0.512 degrees Celsius over molar, and then using that I can find out molality. Divide both sides with 0.512. When you will do that, your molality should come out 12.5 moles. I'm done with step number 2, which was molality. My step number 3, what I have to do, in step number 3, I will use my molality and the mass of the solvent to find out the moles of the solute. So molality is moles of solute divided by kilogram of solvent. I know my molality value from here, which is 12.5. Moles of the solute, I don't know that. Kilograms of solvent. Here in kilograms of solvent, so how much solvent is given to me? We are using 1 liters of water. 1 liters of water basically means 1 kilogram of water. Why? Because the density of water is 1 gram per ml. So that means divided by 1 kilogram. That means what will be my moles of solute then? Moles of solute will be 12.5 times 1, which is 12.5. That's my step number 3. Last, step number 4. In step number 4, I have to convert my moles of solute. Using moles of solute, I have to find out the molar mass. And how do you do that? What is molar mass formula? It is grams over moles. So, do I know the grams of the solute? Yes, it is 575 divided by the moles, which is 12.5, which will be 46 grams per mole. Now, if you will calculate the molar mass for methanol CH3OH, it is going to be 32 grams per mole. For ethanol, it is going to be 46. For butanol, this one is 74. I'm just adding all the atomic masses. So that means my unknown is going to be ethanol. The last colligative property that we are going to discuss is osmosis, and you must have studied osmosis in your biology classes, that it is moving of the particles from the low concentration side to a higher concentration side through a semi-permeable membrane. So, and what is osmotic pressure? It is with time when a greater number of water molecules will move into the solution, increases its volume. So the difference in the height of the solution basically corresponds to the osmotic pressure. Now this is also a colligative property, and the formula for that is this where you say pi written, this basically that is an osmotic pressure, which is denoted by this letter that looks like pi. This one is osmotic pressure, and pi v equals nRT. N is the number of moles, V is the volume, R is a gas constant, and T is the temperature. And if I take this V on this side, it will be N over V, and N over V becomes M, uppercase M, which is molarity. So ultimately, your formula becomes osmotic pressure equals to molarity times R times T. This R, gas constant, its value is 0.08206 liter atmosphere per Kelvin mole. T is the temperature, and this temperature has to be in Kelvin, and M, uppercase M, is molarity, which is the moles of solute divided by volume of the solution in liters. So if you look at this question, calculate the osmotic pressure of a 0.0150 molar solution of glucose at 25 degrees Celsius. You have to calculate pi equals mRT. This is a very simple problem. You are given M value, which in most cases is not, you have to find it. R is constant 0.08206, and temperature is 25 degrees Celsius. Change it to Kelvin by adding 273.15, and when you're going to solve it, it is going to be, answer should be 0.367, and since it is atmospheric pressure, the unit will be atmosphere. So far we were discussing about the colligative properties of non-electrolytes, means when you are adding a solute that is non-electrolyte, it is not breaking down to produce any ions. So, but then now we're going to study about what if you are adding the electrolyte. Now here, so let's talk about electrolytes versus non-electrolytes. Non-electrolytes dissolve in water as molecules. So means If you are adding 1 mole of something, 1 mole of the solute, that results in 1 mole of dissolved particle. Electrolytes, if it's an ionic compound, most of the electrolytes are ionic compounds, they dissociate into ions upon dissolving or ionizing aqueous solution. For example, if you are adding 1 mole of sodium chloride, then 1 mole of sodium chloride dissolves as 2 moles of particles. 1 mole of sodium ion and 1 mole of chloride ion. So that means, and again we said the colligative properties do not depend upon the identity of the solute, it depends on how much you are adding. So 1 mole of sodium chloride basically means you're dissolving 2 moles of particles. So more you add, more will be the depression in the freezing point. So here if you have a question, rank the following aqueous solutions in order from largest freezing point depression to smallest, then first thing you have to look whether these molecules, which ones are molecules, which ones are ionic. 1 molar, so consider 1 molar particles for each. The first one is alcohol, it's an ethanol. So when you are basically adding 1 molar, means 1 mole of this, that means it is just having 1 mole of ethanol in the solution. When you are adding 1 molar aluminum sulfate, means 1 mole of aluminum sulfate in 1 liter of the solution, then 1 mole breaks down into 2 moles of aluminum ions and 3 moles of sulfate ions, which means basically you have 5 total ions per unit, means per one unit of aluminum sulfate, 5 ions per unit. Here you had only 1 per unit. I'm not even going to say ion, 1 particle in the first case. In the second case, basically you are adding 5 particles. In the third case, sodium bromide is an ionic. 1 mole of sodium bromide will produce 1 mole of sodium ion, 1 mole of bromide ions. So basically you are adding 2 ions per unit. Calcium chloride, 1 mole of calcium, 2 moles of chloride. So you are adding 3 ions per unit. So that means where will be the largest freezing point depression? The largest freezing point depression will be here, because more you add, more will be the depression. So that means 1 molar aluminum sulfate freezing point will depress most, then 1 molar calcium chloride, then sodium bromide, and the last alcohol. So these ions that we are calculating here, how many ultimately are in the solution, that basically we give it a name, Van 't Hoff factors. Van 't Hoff factor I is basically how many moles of particles are present in the solution. So if we are adding an electrolyte instead of a non-electrolyte, your all colligative properties formulas will kind of change. And how they are changing, that if for freezing point depression you had Kf times m, then for an electrolyte it will become I times Kfm. For delta, for boiling point elevation, for everything you have to put I on the front. And what is this I? This I is basically these many ions. Calculate the freezing point depression and boiling point elevation of a 0.53 molal. This is molality. Molal means molality of sodium chloride solution in water, assuming 100% dissociation of the solute. So we have to calculate both delta TB and delta TF. Alright, so the first one is, let's calculate delta TF. Delta TF is what? IKFM. How do I know? I have to put I because it's sodium chloride, it's an electrolyte. I value will be 2. And how do I know that? Sodium chloride, one unit of sodium chloride will produce 2 ions in the solution, 1 sodium ions and 1 chloride ions. The KF value, freezing point depression constant, is 1.86 degrees Celsius per molal, and the molality is given 0.53. That is the way you calculate delta TF. And if you have to calculate delta TB, again the formula is IKBM. The only thing will be changing KB. KB is again boiling point elevation constant. It is 0.512 and this value 0.53 is molality. So for delta TF, the answer should be 2 degrees Celsius, and delta TB answer should be 0.54 degrees Celsius. So that's what you have to keep in mind when you are adding an electrolyte. The last question, compare the osmotic pressure of a 0.05 molar solution of sugar and 0.015 molar solution of table salt at 25 degrees Celsius, assuming 100% dissociation of the salt. So let's calculate the osmotic pressure for sugar. First, for sugar, I is equal to 1, because if you are taking 1 unit, then it is going to have only 1 unit in the solution because it's a molecule. So what will be pi? Pi equals to I mRT. I is 1, 0.015 is the molarity, R value is 0.08206, and at 25 degrees Celsius, 25 plus 273 is 298. So pi value is 0.37 atmosphere. For table salt, NaCl, I will be 2 because 1 unit is producing 2 particles in the solution. So pi equals 2. Everything else is same. What is changed? Just the I value, and is going to be 0.73 or 0.74. So that means the osmotic pressure for table salt is more. Of course, why? Because we are adding more particles.